Here we go. Horizontal circles. Basically, the next couple lessons, it's an analysis of horizontal circles and vertical circles. The only difference between these two types of situations is the kinds of forces that are causing inward acceleration.
You mean like gravity would be vertical?
Gravity the vertical circles are interesting because gravity is only impacting it for part of it, because the only time that gravity causes something to act inward is when it's on the top half of the arc.
Bottom half.
The bottom half of the arc, something has to be pulling it up. So that's either a normal force pushing it up or a tension pulling it in. We're not there yet. We're going to deal with that. As far as a horizontal circle is concerned, the horizontal ones are much nicer because that force typically remains constant throughout. Gravity is always pulling down, so it's not pulling into the circle. In a situation like this, as a car drives, so this is top view, looking down, what force is causing my car to turn in? It can only be one.
Steering.
Nope.
Friction.
Friction. Friction on the tires is what causes... No, it's not a force applied. There's no one like outside the car pushing it in to make the thing spin. It's the friction between the tires and the road that causes your car to turn in. If friction just disappears, your car just keeps going straight. This is dangerous driving in icy winter conditions. This happens all the time. No amount of turning, and I've done this, no amount of turning the steering wheel is going to do anything. I remember I was in high school, this is grade 12, I was dropping a friend off at Rick Hansen. I went to MEI. She was at Rick Hansen. We met for breakfast, and I was dropping her off on it. It was a snowy morning. I was trying to get to Hansen. There's curves and there's hills, and it was icy. And I'm going, and there's a four-way stop intersection just past the temple going towards Rick Hansen. And I locked it up, and there was this sheer ice, and I wasn't going anywhere. So I was like, you know what? I'll turn. We'll go down Blue Jay, and I won't die. And I turned the wheels, and the car just kept going straight. And the car itself started to spin, but the whole thing was going straight. It was awesome and terrifying. But the inertia of the car was going straight. The turning of the tires just made the car do this.
Ooh, you're doing like a spinning.
Yeah, it was off.
Spinning teeth.
So I stopped sideways in the middle of the intersection. It was great. So there was no friction causing my car to turn, so I couldn't turn. On a flat surface, typically what you're dealing with is friction. And it's nice, flat circles are good, because typically that force remains constant throughout the entire circle, or whatever portion of the circle you're on. We've got some notation here. We'll jump down to the bottom. The language in the notation that we use is centripetal. Hands up if you've heard the word centrifugal. Like a centrifuge. Okay? A centrifugal, some people are like, oh yeah, it's a centrifugal force. Like, that's not a thing. A centrifuge causes things to spin. It's the inertia we've already established that causes objects to want to remain straight. What that looks like is they want to fly out from the center of the circle. That's not a force that's doing it. That's their own inertia. It's a centripetal force, an inward-seeking centric force. Pedal means towards, century being the center, and inwards force, a centripetal force, is actually what we have acting here. Centrifugal is just the appearance of a force due to the inertia of an object. Okay? Centrifugal, not a thing. Centripetal, actually what's happening here. So there's various notation that we can use. A sub C, F sub C, a centripetal acceleration or a centripetal force acting on these things towards the center, that sub C means. I typically, when I write these things, will call them F sub C and A sub C. I love my subscripts if you haven't figured that out already. The book might not, they'll just call it F net and A. And then contextually, because this is a unit on circular motion, you will then have to understand that F net and A is just what I would call F sub C and A sub C. Given the context of the question. Flip the page. Let's do a couple of these. If not friction, well, what then? Sometimes you might have a situation that looks like this. How many of you have ever seen one of these toys, either in a toy store or maybe you had one of these growing up? No, it's one where you have a plane with a little propeller on the front with a rope attached to the ceiling and it flies itself in a circle. Have you seen these before? No. You haven't lived. Yeah, Toy Story. Yeah. I can't remember.
No, there's a toy like that.
I'm pretty sure you're right, Zach. This thing's not resting on anything. So because it's not resting on anything, we can't deal with friction. It's hanging from something, so we've got a tension upwards and in. So what portion of the tension, or there's portions of the tension here, what portions are doing what? I'll say it that way. Well, what are the portions of tension? Parallel to what and perpendicular to what?
Parallel to the plane?
Yeah, parallel to the plane. So you've got one component acting horizontally, parallel to the path of the plane. We can call that Tx, because it's typically flat in this direction. And then the other component of tension is doing what? It's up. Thanks, Toby. It's going this way. So here's what they are. What are they doing? Right now we can't solve for anything until we can figure out what they're doing. What is Ty and Tx doing? So Tx pulls it in. So Tx is responsible for the circular motion portion of this. Ty, if it's keeping it up, what's it counteracting? Yeah, it's counteracting force of gravity. So by analyzing what they're doing, we can actually now go through and solve this problem. If Ty is countering gravity, that tells us that, I'm going to go on this, and I'll stay over here. Let's do this one first. This implies that Ty equals Fg. So I've got my angle here. How is Ty related to T? Ty is T cos theta. Yeah, good. So I've got T cos theta equals mg. I know what g is. So m is just the mass of my plane. So I've got an expression here. T cos theta equals mg. And I've also, so now dealing with the circular motion piece, I've got some more stuff here. For an object in circular motion, our F net equation still applies. F net C equals MAC. So what are my net forces acting centripetally? That's where the Tx is coming in. So Tx is going to equal MAC. How is Tx related to T? So I've got T sine theta. That's going to equal, I need an expression here for AC. I don't know what my inward acceleration is, but I can relate it to some things I might know. The acceleration of an object in circular motion is equal to what? V squared over r. So I get the expression T sine theta is equal to m v squared over r. So now I've got two expressions. V is just going to be a constant, a property of the plane that's moving this fast around the circle. R is just the radius of my circle. M is the mass of my circle. T is the tension, and theta is the angle. Sorry, the mass of the plane traveling in the circle. Sorry, did I say mass of the circle? Mass of the plane traveling in the circle. So we've got these two expressions that are going to end up being very, very useful. That I crammed into a very small area. No, I would not write those on the formula sheet. It's going to become useful for you to become comfortable deriving those. So flip the page. Let's actually do this question. Actually, we'll do some more things with this question. There is a relationship that we are going to write down. Okay, so we already have this. That's my tension. This is my FG. We're just going to write, that is our free body diagram. Done. Okay, if you're asked to identify a free body diagram for the plane, that's it. Why don't I include the inward and upward pieces of tension on a free body diagram? Because they're components. Good. They're components, so I don't include them on a free body diagram. But they're useful, so let's add them after we've got our free body diagram. So I've got this guy here. We've already established what these are. This is Tx, which is equal to T sine theta, and Ty, which is equal to T cos theta. The plane is in equilibrium as it flies around the thing. So that means my forces up are going to equal my forces down, which tells me that T cos theta is equal to mg. We also know, so now we had all those expressions before, forces up equals down, forces left equals right, torques were balanced. There's a fourth one now we're going to add to this. We're going to drop, some of the rest of the ones aren't useful, but there's a fourth one here. This object is in uniform circular motion, which I'm going to abbreviate as uniform circmot. Okay, uniform circular motion, which tells us that F net C equals M A sub C, and that A sub C is equal to V squared over R. The only force acting in the direction of my circular motion is this guy here. So we're going to get T sine theta is equal to mv squared over r. I'm going to call this equation 1. I'm going to call this guy here equation 2. For reasons that are going to become evident here in a second, I'm going to take equation 1 and I'm going to divide it by equation 2 just for fun. So that's going to give us T cos theta. Oh, no, I lied. Nope, I lied. It's 2 over 1. Sorry. It's 2 over 1. Yep, my bad, sorry. So it's going to be T sine theta equals mv squared over r divided by T cos theta equals mg. Look at what's going to happen here. Some things are going to cancel. What's going to cancel, Gersa Hill? My tensions are going to cancel. What else is going to cancel? My masses are going to cancel. Sine theta over cos theta equals tan theta. So tan theta is going to equal v squared over rg. This is a fun little result. This tells you that the angle theta has no bearing on the mass of the object spinning. It is only dependent on the speed that the object is traveling in the circle, the radius of the circle on the planet that you're on, which is a neat result. If you wanted to, I'm not going to write that on the formula sheet, but if that you want to toss that on the back in the section devoted to circular motion, that might not be a terrible thing to keep handy. Or you could, you can derive it yourself every time, but the relationship, it's handy to have. Okay, so that's one kind of flat circle. Let's go back to the sitting on a surface kind of thing. The picture below shows a frictionless tabletop in top view, so top looking down on it. The mass is 4.15 kilograms attached to a 2-meter long string. It is moving at 2.5 meters per second. We want to write the force equations and solve for the tension in the string. So, the picture there demonstrates that this object is in circular motion, so that's where we're going to start. Uniform circular motion implies F net C equals MAC and AC equals V squared over R. Just like dynamics where you started with F net equals MA, but now we've got a different expression for our acceleration. The only force acting on the mass here, pulling it into the center, is this string. So that's going to be our tension right there. So the only force acting in is T. That's going to equal mv squared over r. Now I can just insert some of these values. T equals 4.15 kilograms. We're told that the speed around the circle is 2.5 meters per second. I square that, and the radius of my circle is 2 meters. It's a large circle. So what's the tension in the string have to be?
$12.97.
12.97 what? Newtons. That is not a lot of force. That's the tension required to spin that object. And now for something yet entirely different again, flip the page. We've got tension pulling in on a flat circle. We've got components of tension for a flying object. Now let's deal with friction. The picture doesn't look great because it's hard to draw a three-dimensional situation at an angle on a flat piece of paper. But what's happening here is this is supposed to be a flat piece of road, and you've got a car driving the circle. So what forces are acting on my car? We've already established that what's acting in? There is no rope attached to my car. I asked what force was acting. Force of friction is acting in. Okay. It would be tension in what kind of scenario? There was a rope. This happens in superhero movies. I feel like Batman did it. Batman's driving straight. He shoots a cable off the side of his car. The cable hits a building. Goes around the circle. Okay? In this case, this isn't Batman or the Batmobile. It's just a dude driving on the road. So because there's no rope being launched off this or cable launched out of the side of the car, the only thing that can act to push this thing into a circle is friction. What other forces are acting on the car? Gravity down, I guess into the road, and normal force upwards. That is it. There's nothing else acting on our object. No. That's the force of friction. It's all friction. Friction's moving you forward, friction's moving you in. So, like the plane question, we're going to do a bunch of we're going to analyze the situation using a bunch of variables we don't know, and we're going to come up with an interesting result. So, we know a few things. We know the car is not being launched up into the sky or being driven down into the ground. So my forces up have to equal my forces downward. Also, this is following a circular or a round flat corner. The implication there is that this is a portion of a circle. So for at least part of this scenario, we've got uniform circular motion. So the implications of this are what?
Fn equals
Okay, I've got Fn equals Fg, which means that Fn equals mg. Okay. Now my uniform circular motion tells me what? F net C MC. Keep going, Blake. Okay, keep going.
where F net will be
Keep going.
mg equals mg squared over r.
That's not true because Fn is not force of friction.
U,
Okay, so force of friction equals mu Fn, okay? Mu Fn equals mv squared over r. Keep going. So mu mg equals mv squared over r. Keep going. My masses are going to cancel. And the interesting result here is we're going to divide both sides by g. To isolate mu. So mu is going to equal v squared over rg. So the coefficient of friction required to make this corner is determined by, has nothing to do with the mass of the car. It has everything to do with the speed at which the car is going, the radius of the circle, and the planet that you're on. Also it has interesting engineering implications. Doesn't matter what the mass of your car is. It has everything to do with the coefficient of friction. And how do you change the coefficient of friction for a car? The tires. So this is all about engineering a tire to maximize the coefficient of friction between it and the surface of the road. And that'll depend on different circumstances. If the road is dry, the tire that's going to give you the max amount of friction is perfectly smooth.
Oh, true.
If the road is perfectly dry and perfectly smooth, the tires that you want is going to be also basically perfectly smooth. None. That's why if you look at like summer tires have really thin tread compared to a winter tire because you want to stick to the road as much as possible. If you guys watch F1, racing tires are super smooth, but they're useless as soon as it starts to rain. So this is why different tires have, well, and even it comes, I've been watching, no, I don't, there's a Netflix documentary. It's not Top Gear. I can't remember what it's called. But like you watch the pits, and they pit stop, and they change their tires as the race progresses. As the tires heat up, it changes how they stick to the surface. So you change tires partway through a race.
But they only get a certain amount of tires as well, which then...
So it's all about the strategy of changing tires. So, and then none of that has to do with the mass of the car. It all has to do with the style of the engineering of the tires and how those tires are going to heat up. So it's a very interesting engineering application to something as simple as this. You know, and racing is a billion-dollar industry, multi-billion-dollar industry, governed by something as simple as this. The speed at which you want to make a corner is going to dictate the kind of tires you have to have. Yes, have a good physio appointment. The rest of this video will be posted online. Interesting, whether you see it or not. Okay, now, there's a technical comment here, and I think this is the last little bit. The reason, so I guess, so this comes back to kind of what you were saying before. You're questioning about this. The reason that friction is inwards has to do with how wheels actually end up working. When you turn your front wheels to turn the car wants to keep going straight, and so the wheels push hard on the road in the direction shown. So you're driving straight, you turn the wheels. What ends up happening is the wheels are pushing back on the road kind of at an angle like that. So the road ends up pushing back on them like that. Newton's third law, every action has an equal and opposite reaction. As the road pushes back on them, it's going to cause the front of your car, basically you're creating a torque on the body of the car. It's causing the front of the car to follow this inward path. Once you start to follow that, so the friction force from the road, what I've drawn here is this piece here. Your tires are pushing back, so the road pushes back. Your car follows this, torquing effectively around the middle of your car. Hey, Priya. Come on in. You can leave that on the desk. If you can stop by tomorrow right around the same time, I'll have an envelope with money for you in it. Just give it to Crystal back there. Yeah. Thanks for stopping in. Cool. We cool with how, just a rough approximation of how this is going? Okay. Basically an engineer. So I want to give you guys a couple questions that are applications of this style of problems. You got the hanging and the spinning and the flat surface and the frictionless flat surfaces and the frictioned flat surfaces. I want you to work on these problems here. You're going to do 1 to 3. Sorry, 1 to 3. Got to make sure I give you the same ones that I always give. No, it's more than 1 to 3. 1 to 3. No, we've already done 4. You're going to do 5. You don't have to do 6 because we've already done 6. You're going to do 9. And that's it. That's it.
Let's go.
Yeah. There you go. That's it. 1 to 3, 5, and 9. Yeah, go for it. Practice this stuff. You've also got a test tomorrow. So whatever would be the best use of your time for the next 35 minutes, feel free to do that. Tomorrow we will be doing lesson 3, vertical circles tomorrow, after you guys are done the test.